outer ear is the most lateral part of the ear and is the only physically visible part of the auditory system. The temporal bone lives up here, right here in my head, and it holds the external auditory meatus, which allows sound to travel down the canal to communicate with the middle and inner ear. The function of the outer ear is to gather sound from the acoustic environment and funnel the acoustic energy to the auditory mechanism, which goes in right here and down the canal. There are 5 basic parts of the outer ear. The pinna, which is its chunk right here, which is used to help improve sensitivity to high frequency sounds at 3000 Hertz. The helix, which is this chunk right here, marks the most distal borders of the ear. The antihelix, which marks the entrance to the concha. The scaphoid fossa is up here. And the 2 concha, the Simba concha and the Calvin concha, which both help to aid in our ability to localize sound sources, and the sound helps to funnel into the external auditory canal. The external auditory canal, which is this part right here, is the next structure acoustic waveforms have to move through to get to the middle ear. It allows air to warm prior to reaching the tympanic membrane and conducts acoustic signal. It also amplifies speech frequencies from around 2000 to 7000 Hertz. The external auditory meatus is where serum glands are found and wax is produced. Serum or wax is very important because it protects our auditory system from foreign objects and helps in the natural cleaning process of the ears. The ear canal is split in 2 parts. The first, the lateral chunk here, is cartilaginous, which supports the serum glands, is lined with hair, and has a protective function, while the medial 2/3 is the bony portion, the mastoid air cells of the temporal bone encase. The tympanic membrane is located at the end of the external auditory canal. It is the first mobile link in the auditory chain of events. The function of the tympanic membrane is to aid in sound transmission to the inner ear. It has a manubrium of the malleus, an umbo of the incus, which is the most concave part, or the most medial part, to the middle ear. The annulus is the outside layer of the ear, the outer membrane, and the cone of light, which is from an otoscope. The pars flaccida is up here, and it is a flat part of the ear, and while pars tensa is 3/4 of the tympanic membrane, and it is rigid. There are 3 layers to the tympanic membrane. The outer layer, the central layer, which is fibrous and full of connective tissues, and the most medial layer, which is closest to the middle ear.
Immediately following the tympanic membrane is the acicular chain, which is made up of the malleus, the incus, and the stapes, which are 3 of the smallest bones in the human body. The middle ear is made up of 6 walls. I'll start with the superior wall, also known as the ceiling. The most important landmark on the superior wall is the tegmen tympani. The inferior wall, also known as the floor, houses the jugular fossa. The tympanic membrane and the squamous portion of the temporal bone can be found on the lateral or membranous wall. The medial wall has many important landmarks. The oval window, which is directly under the footplate of the stapes and allows access to the inner ear fluids of. There are 2 important muscles found in the middle ear. One of them is the stapedius muscle, and the other one shown here is the tensor tympani muscle. The middle ear is an air-filled cavity responsible for converting acoustical energy in the form of sound waves to mechanical energy. The middle ear is most popularly known for being an impedance matching system. The ratio between the diameter of the tympanic membrane and the diameter of the oval window is 17:1. Lever action of the ossicles, tympanic membrane, and the umbo helps to explain this phenomenon. The eustachian tube is responsible for equalizing ambient air pressure and air pressure within the middle ear for the removal of debris from the middle ear.
Here is the inner ear. It's made up of the cochlea, the vestibule, and the semicircular canal. Each part plays a role in hearing or the vestibular system. The vestibular system also accounts for things as spatial orientation, motion, and equilibrium. Let's start with hearing. The cochlea is the last area of the auditory pathway before sound reaches the brain. The cochlea is located in the auditory apparatus. It is made up of several parts. It consists of the bony labyrinth and the membranous labyrinth. Together, the spiral takes about 2.5 turns. Okay, you can stop. The bony labyrinth holds the scala vestibuli, which starts at the oval window, and the scala tympani, which ends at the round window. Both sections of the bony labyrinth are filled with perilymph. The two parts of the bony labyrinth meet at the helicotrema. Membranous labyrinth is made up of the scala media, or the cochlear duct, and is filled with endolymph. Inside the cochlear duct, the organ of Corti is housed. Above and below the organ of Corti are two important membranes, the basilar membrane and Reisner's membrane. All of these parts of the cochleus wrap around the modulus, which supplies blood and the nerves to the cochlea. Vestibular system. The vestibular system, made up of the vestibule and the semicircular canals, is responsible for your sense of movement. It works closely with your brain and eyes to perceive where you are in space, maintain equilibrium, and detect motion. Since the vestibular system is a paired organ, your semicircular canals and the rest of your vestibular system have mirror twins on the other side of your head. This is especially important for the semicircular canals. Because they are flipped, they experience the same liquid movement in mirrored canals. This means that while one half of the system, say your right side, is in action, the canals of the left side are inhibited. This inhibition never happened, you'd be perpetually dizzy and face other vestibular problems. The vestibular system is amazing at adjustment. It follows the basic laws of physics, but on top of that, it also relies on other systems, such as touch and sight, to ensure it isn't tricked. Like when you ride a roller coaster. Your vestibular system doesn't stop working, even though your direction is rapidly changing. Its ability to adapt is so profound that it only takes astronauts a short period of time to adjust to weightlessness once they are in space. Their systems take all the same feedback that ours do to provide them with spatial awareness, and still maintains equilibrium even though they have significantly less gravity acting upon them.